to the cloud. Perfect. So thank you everyone for joining us. Thank you, Dr. Yendiki. Am I saying it right?
Yes.
Yeah, for kindly accepting the invite and taking the time to give us a talk on this important topic. So a quick brief bio. Dr. Yendiki is an associate professor in radiology at Harvard Medical School and associate investigator at the Massachusetts General Hospital in the Atheneola Martinos Center for Biomedical Imaging. Her background is in electrical engineering with a specialization in statistical signal and image processing. She is the lead developer of Dracula, which stands for Tracks Constrained by Underlying Anatomy, the Diffusion MRI Analysis Toolbox in the FreeSurfer software suite. She had spearheaded the Iron Track Challenge, an initiative bringing together tractography developers from around the world to compare and optimize the accuracy of their methods using gold standard postmortem data. So this is I think most of the talk for today, very fascinating and highly QC relevant. And she's been an MGH site PI for the NIH Connectomes related to human disease and PI of 2 R01 awards on postmortem validation and integration of diffusion MRI with microscopy. Without further ado, Dr. Yendiki, please take
Thank you so much. Thank you so much, Pradeep, for the invitation. 1 second. Okay, so people can see my screen. Everything okay?
Yes.
Okay, great. So I am a member of the FreeSurfer development team. And specifically, I work on the diffusion analysis component in FreeSurfer. So you probably know the structural stream in FreeSurfer, Recon-All, which allows you to process T1 weighted images, reconstruct surfaces, perform cortical parcellation, and whole brain segmentation. With the diffusion stream, we perform pre-processing of the diffusion weighted images. We also produce some QA measures that I will get to in a little bit. And then the data, the diffusion data, are combined with the structural segmentation from the T1 scan of the same subject to perform global probabilistic tractography with anatomical priors, reconstruct a set of tracts of interest, and we can also, once we have done that for every individual, we can also do a long tract statistics of different diffusion measures for the different tracts. Our approach for reconstructing these tracts of interest is a Bayesian framework that combines a term that tries to fit the shape of the tracts to the diffusion orientations from the subject's diffusion data. This is the likelihood term over here on the left, as well as a term that tries to fit the shape of the tracts to prior anatomical information from the anatomical literature on these on the neighboring structures of these tracts. So instead of including ad hoc ROIs to constrain the tracts, what we do is we fit the shape of the bundle simultaneously to the diffusion orientations and to the anatomical neighbors from the structural segmentation. So basically, we learn from a set of training subjects how often this tract that we're trying to reconstruct, let's say the anterior thalamic radiation in this case, goes to the left, the right, anterior, posterior, etc., of each of the structural segmentation labels from the FreeSurfer APARC and ASEG. In the first version, we started kind of humble. We just had 18 tracts that covered only 18% of white matter. And in the latest version that was released this past July, we have 42 tracts that cover 82% of white matter. it's not just the number of tracks that increased the coverage, it's that in our old version, for the manually labeled training data, we had used conventional data that was available 10 or even more years ago. And in the new version, we are using data from the connectome scanner from MGH, from the Human Connectome Project, to perform the manual annotation of the tracks and to train Dracula. So the idea is to use this very high quality data to train the algorithm, but then apply it to conventional quality data that can be collected on any scanner by any regular study. Oops. So the idea is to improve the models of these tracks that we have from this manual annotation on the MGH connectome data that was collected on the connectome scanner with a maximum B-value of 10,000 and 500 plus directions, and then use Dracula to perform automated reconstruction in conventional data like B equals 1,000, 64, 32 direction data, which is closer to what most studies have used. What we found in this paper by Chiara Maffei that just came out in your image just a few weeks ago, actually, is that the automated reconstruction in the more regular quality data, B equals 1,000 in either 64 or 32 directions, can reach up to 89% sensitivity with respect to the high quality manual annotations from the connectome data. However, this sensitivity is reached at the cost of different levels of reconstruction error for different methods. And by reconstruction error here, I refer to the distance between the automatically reconstructed tracts in the B equals 1,000 data and the manually labeled tracts from the B equals 10,000 data in the same subject. So for Dracula to reach this 89% sensitivity with respect to the high quality data with just 64 direction data, it required a reconstruction error of 3.5 millimeters. And this reconstruction error went up a little bit by about 20% to reach the same sensitivity with half the directions. But with a conventional multi-ROI method that just constrains the tracts by some ROIs from an atlas, that reconstruction error was much higher, both in the 64 direction data and in the 32 direction data. So with our approach, we are able to use these high quality data that can only be acquired in a connectome scanner, that there's only a handful of those in the world, and use it to improve reconstruction, automated reconstruction of the tracts in regular quality data that are feasible for clinical studies.
Can we interrupt you?
Yes, yeah.
Okay, can you go back a slide?
Yeah.
So it's interesting you use the metric sensitivity instead of accuracy. Do you want to like elaborate more on that?
Yeah, so that is the rate of true positives. So voxels that are in the automated reconstruction that are also in the automated reconstruction, the B equals 1,000 data that are also in the manually annotated labeled the same tract in the B equals 10,000 data. So it's a measure of the coverage of the ground truth tract from the high quality data when you use the low quality data for automated reconstruction, if that makes sense. So you can kind of like a true to false positive trade-off here. So you can achieve very high sensitivity, very good coverage of the true tract if you allow the tractography to go crazy, but then it'll have a high reconstruction error because the reconstruction error is the maximum distance of the automatically reconstructed tract to the ground truth tract. Does that make sense?
Yeah, it's very interesting. You know, I guess I come from an anatomical segmentation world. You know, I'm starting to think, why not a dice coefficient? You know, and
yeah. So the dice coefficient would be another way to quantify this, but there would still be a trade-off there with all these methods as you increase or decrease the threshold of the tractography. So you can't really capture this trade-off with just one measure. You need two measures to capture the trade-off. Kind of like an ROC, think of it as an ROC curve, if that makes sense. Is that okay?
Yes.
Okay.
Thank you.
On that note, I wanted to put in a little plug for Brain Hack Boston that's going to be held on December 6th and 7th, so coming up in a couple of weeks. It's held jointly with Brain Hack Nordic. We're doing a hybrid model of some of us are going to be on site at MGH, but we also invite virtual attendees, and MGH right now does not allow visitors, so that the on-site component is only for employees, unfortunately. So we're trying to make it fun. Bring your ugly Christmas sweater. One thing that I'm planning to work on is make Dracula more interoperable with the BID standard, so allow it to read in easily data sets that are in BIDS format. And anything else that, any other ideas that, let's say, about QC that we might come up with today, we can work on then. So going on to the QC stuff. So this was work that we did a few years ago, trying to quantify the effects of head motion in diffusion MRI. Obviously, we know that head motion is bad for any kind of neuroimaging, but for diffusion MRI, it's especially bad because the contrast in the diffusion weighted images has to do with the microscopic movements of the water molecules. So if on top of these microscopic movements, we also add a microscopic movement of the head, this can be encoded in the intensity values of the images. So in addition to the typical misalignment that we get between the consecutive diffusion weighted images as the subject is moving their head, there's also another type of effect that we have in diffusion weighted images that sometimes we see some of these super dark slices. So we have intensity dropout in individual slices if the head motion occurred while the diffusion encoding gradient pulse was being applied. And so obviously we can correct for the misalignment between consecutive volumes by registration, but this kind of intensity dropout is harder to correct. Because head motion tends to happen randomly in different directions, it tends to lead, as I'll show you in some of the results that we got, to an underestimation of anisotropy. So it looks as though the water molecules are able to move in more directions, hence lower anisotropy, just because the subject is moving their head more. And this can lead into false positive differences between subjects and between groups when one group moves more than the other. The effects of this get more and more severe as we go to higher and higher B values, especially for this dropout, intensity dropout issue. And obviously, as we get to longer scans with more directions, high resolution, etc. So the results that I'm going to show you were from a few years ago, and we used data with a relatively low B value. So it was just a single shell with B equals 700. So you can imagine that all the results that you're seeing are probably going to be worse with higher B values. These are the motion measures that we computed in that paper and that are also automatically computed by Dracula during its pre-processing steps. So the first is the conventional between volume motion. So the average translation and the average rotation between consecutive diffusion weighted images. And then some within volume motion measures that have specifically to do with this dropout effect that's specific to diffusion MRI. So the percentage of slices in a scan with signal dropout and the severity of the signal dropout. So we had these four measures. And then we put them all together in what we call the total motion index, or TMI, where we took these measures 1 through 4, corrected them, centered them by their mean, and then divided by the interquartile range. So that, because these measures all have different units, so you can't just add them all up. So we use this as kind of a composite measure of data quality. And this used data from Nancy Kanwisher's lab at MIT from a study of children with autism spectrum disorder and typically developing children. So we looked at anisotropy and diffusivity measures in different tracts that were reconstructed with Dracula in different subsets of these subjects. There was something like 200 plus scans. So at every time we chose 30 and 30 subjects, from 30 from the autism group and 30 from the typical group. In the cases where there were only small differences between the subjects in the autism and the subjects in the typical group, this is what the differences in fractional anisotropy, mean diffusivity, radial diffusivity, and axial diffusivity looked like for the different tracts. So everything you see on the x-axis here is a different tract. This is from the old Dracula Atlas, so it's just 18 tracts. And what you see here is the percent difference between the two groups. And we repeated this for many combinations of 30 and 30, and this is averaging the results over cases where we happened to pick 30 and 30 that had similar amounts of head motion between the groups. In the cases where we were unlucky and we happened to pick subjects where there was much more motion in one group than the other, we saw that these differences in anisotropy and diffusivity increased, specifically the differences in radial diffusivity seem to go up, and the differences in axial diffusivity seem to go down, and the differences in fractional anisotropy went down. This makes sense because when the axial goes down and the radial goes up, the two become more similar, and hence the anisotropy becomes lower. And these differences that had to do with whether there was a large difference in head motion between group or not were more severe for some tracts than others. So for the forceps major and minor of the corpus callosum, as well as for the cingulum bundle, we found that this effect was more pronounced. So one might ask that, well, maybe there is something biologically different between these subjects with autism that move more. So how do you know that this is not a natural biological effect? So then we repeated this experiment, choosing randomly 30 and 30 subjects from the typical children, from the control group only. So this is only 30 controls versus 30 controls, and we're picking different sets of 30 every time. In the cases where we had very similar head motion between the two control groups, we basically didn't see any differences in FA, mean radial and axial diffusivity. And in the cases where we happened to pick 30 and 30 subjects where there was much more head motion in one group than the other, we saw similar effects as in the autism versus typical comparisons. So this does seem to be an effect due to head motion and due to having differences in head motion between the groups. So it can potentially lead to false positive differences between populations because we haven't controlled for the motion. These results are all after the typical registration-based motion correction is applied, where we realign all the volumes to the first one. So doing that did not fix this issue. The general trend, as I mentioned, was as the head motion went up, the radial diffusivity appeared higher and the axial diffusivity appeared lower. As a result, the mean diffusivity was not affected so much, but the fractional anisotropy went down with more head motion, at least in our data. One thing we showed in that paper is if we use that composite measure of motion, the total motion index that I showed you that we got from all those four measures of both between and within volume motion. If we use that total motion index as a nuisance regressor in our group comparisons, we dramatically reduced some of the false positive differences due to head motion. And this shows the importance of, first of all, quantifying the amount of motion. And then the first thing to do would be to simply compare the groups to see if there is a group effect in terms of head motion, or if you're looking at correlations with some behavioral or clinical variable to see if there are correlations between that variable and motion. And if you do see an effect, then it's important to include the amount of motion as a nuisance regressor in any group analyses. So any questions about this stuff? Are there questions in the chat?
No, so far.
Okay. Yeah, so these are the measures that we produce as part of the pre-processing in Dracula. And then it is, at this point, it really is up to the user to decide what to do with them. Like, we don't throw out any data by default, but the user can look at the subjects, look at the different motion measures and decide if there are subjects that are outliers, if they want to get rid of them, or sometimes this may not be possible because those might actually be the more severe cases in the disease group, for example. So in that case, it's always important to include motion in the analysis the way you would include like age or sex or whatever, or IQ. Right,
so maybe I can ask a question here. It's very interesting. The discussion is at the group level, you know, because outliers requires a group to be decided whether it's an outlier or not, for example, right? And the trends that you show here, you know, with increased motion, you see RD increasing, AD decreasing, etc. So can you comment more on the individual level QC?
The differences are not huge. So the differences in terms of the head motion are actually very small. So it wasn't like there was a big outlier or something like that. There was actually quite a bit of range of movement in these children. You know, they were like 5 to 12 or something like that. So very difficult age to scan, and especially the ones with autism were moving more. So it was definitely not due to outliers. And one thing we looked at the paper was if we just removed some of the outliers, like did a histogram of the different motion measures and just tried to throw out some of the ones that had high motion measures. But what I found, and I you know, checked each one visually multiple times to give them kind of a grade. It was hard to find a threshold where you would throw out all the bad subjects and you would not throw out any of the good subjects. So it did not seem like it was easy to just throw out some outliers and get rid of this problem. It was more of a continuum.
Yeah, so that's actually one of the goals for the special interest group to, you know, have some kind of protocol to have like a levels of quality, so to say, you know. But I think developing that kind of consensus requires the community get together and assess it, you know. So we have another question in the chat. I don't know the name, I just the username, but how does the pre-processing in Dracula compare with FSL Eddy pre-processing? Oh yeah, so for the pre-processing, we use all the standard tools that are the industry standard at the moment. So you can use Eddy from FSL. You can either, if you have data that were collected with reverse polarity, you can use Dropout, or if you have field maps that were collected separately, you can also perform field map based correction. Right. And the follow-up question is, are eddy currents, distortions, and movements calculated at the same time?
Yes, so typically those are, whether you do it with the old style, just simply registering the different volumes, or whether you do it with a model-based approach like Eddy, those always come out at the same time.
Thank you. Do you want to follow up the user whoever asked the question? Does that answer the question? Okay. Yeah.
Oh, hello, thank you. It was good. Thank you very much.
Okay, so far I've been talking about ways in which the data quality can mess up our results. Oh, and I should say, I forgot to mention that this study focused on, FA, mean radial axial diffusivity, like track-based diffusion measures, but then other groups have also looked at the effects of head motion in connectivity matrices. For example, this paper of Baum et al. In Neuroimage looked at the weights of edges in sort of, whole brain graph theory analysis, and showed that there's a big effect there too. So the head motion decreased the weights of edges with high intersubject consistency and increased the ones with low intersubject consistency, and the effects were different for longer and shorter connections. So it's important for all types of downstream analyses. So I talked about, things that can go wrong in our results, in our studies, because our data quality is an issue. But there are cases where even with the perfect data quality, tractography would not give us the right answer. And that's where all the validation stuff comes in. So why, as the data quality improves, with the Human Connectome project and with these new scanners, we can collect very high SNR data with high spatial and angular resolution and high B values. So as the state of the art has improved in terms of the acquisition and given us both higher SNR and higher resolution, we can get very accurate estimates of diffusion orientations. However, this has not solved all the problems with tractography. And the reason is that the spatial resolution is still in vivo limited to, at best, about 1.5 millimeters. And there will typically be more than one axon population in a 1.5 millimeter cube of tissue. And we are unable still to resolve certain types of microstructure, certain types of fiber configuration, even with very accurate estimates of diffusion orientations. So all of these three different configurations that I show on the left will give us an orientation distribution function that looks similar to this. And the result is that when a tractography method will reach this voxel, let's say from the bottom edge of the voxel, it will not know which of the peaks of the ODF to follow, because it does not know which of the three configurations on the left are correct. And this is something that would persist even with perfect data quality. So even if we had continuous space, infinite SNR data, this problem would persist. And this has to do with the fact that when we reduce the data to an orientation distribution function, we have discarded some of the information that would presumably allow us to distinguish between these fiber configurations. So because of this, the tractography method has to make an arbitrary choice, and typically it will choose to go as straight as possible. This is how methods are usually configured. And this means that it will essentially be choosing the configuration on the far left, so the crossing. And a lot of the focus of the community has been in improving the modeling of crossing fibers. But the issue is that many other configurations will have similar ODFs, and just based on the ODF, we will not be able to distinguish them from the crossing. So because of these arbitrary decisions that have to be made between the different peaks of the ODF at every step, at every voxel, this will lead to some anatomically meaningless connections, even in very high quality data. So this is a data set from, the Bmax equals 10,000 data from the Connectome scanner. And this tract that I'm showing here is something that came out because the tractography was, walking along the corticospinal tract, and then it took the wrong turn. It jumped from the corticospinal tract to the corpus callosum, and then on the other side, it jumped back to the corticospinal tract. So this is something, it's a tract that even with very little anatomical knowledge, you can see it and you can say, okay, this is probably wrong. But for many other tracts that we see in the brain, we don't know if they're wrong or right. And that's why even with the increasing quality of our in vivo data, we still need postmortem validation where we can have ground truth of the anatomy. There are a few different ways of getting ground truth for tractography and for diffusion orientations. And it's important to know that none of them is perfect. None of them will give us all the information about all the fibers in the entire brain. Gross dissection is one of the classical methods where the axon bundles are physically extracted one by one from fixed tissue. And it has been used to establish the presence of the large white matter pathways, like the inferior longitudinal fasciculus, the superior longitudinal fasciculus, the uncinate fasciculus, et cetera, to show that every brain has one, and that the general overall shape of these pathways is similar to what we get from tractography. However, this approach is not so practical for mapping finer details. So for following smaller bundles as they make their way through these large highways, for following the axons all the way to their endpoints, and for deriving crossing angles between pathways, because it's a destructive method. So in order to dissect one bundle, you have to destruct the others that are crossing with it. Myelin staining has been used to give us estimates of the local properties of myelinated axons within a slice. So they give us all the orientations of all the axons that are crossing or branching or what have you in a certain area. It gives us this information typically in plane. And it's because of histological distortions and nonlinear distortions slice to slice, it's very hard to follow axons. Not impossible, but hard to follow axons, axon by axon, from one slice to the next. It's a very difficult nonlinear registration problem. Anatomic tracing is used in non-human primates. There, the tracer is injected in vivo in the gray matter. And it propagates through the axons, aided by motor proteins that transport chemical energy for metabolism. And that's why it has to be injected in vivo. Then it's given time to propagate through all the projections from the injection site. In a macaque brain, this can take about 2 weeks. Then the animal is sacrificed, the brain is fixed and sectioned, and then the sections undergo histological processing to visualize the tracer. And the type of processing can vary by the type of tracer. Newer tracers that are visualized by an immunohistochemical reaction, and some examples are shown here, lucifer yellow, fluororuby, etc., allow us to visualize both the terminals as well as detailed axon morphology. So some of the older material, some of the older tracers showed only the terminals, and so could only be used to validate sort of the connectivity matrix, what is connected to what. But these types of tracers allow us to follow the axons from the injection site to all their terminations. A limitation of this approach is that you cannot get the full connectivity diagram of an entire brain. We can do, because there's 3 different tracers that do not interact with each other. At best, we can do 3 injections per brain in different areas. And this is very appropriate for validating tractography, but not so much for validating orientation distribution function, because it labels all the axons in a single fiber population that goes through a voxel. It doesn't label all the ones that are crossing with it. And also this approach, is not feasible in human subjects. So some newer optical imaging methods have been developed in the last decade or so to directly image axon orientations in human brains. These approaches can also be applied to animals, but the important thing here is that they're applicable to human tissue, unlike anatomic tracing. These methods rely on the birefringes of myelin. So when polarized light goes through myelin, a phase retardation is induced that depends on how the axons are oriented at every location. One method that relies on the birefringence of myelin is polarized light imaging, or PLI. It has been demonstrated not just at the 10 micron resolution that I'm showing here, but at even higher resolutions. And it's applicable to large fields of view, like the whole brain that I'm showing here. In this case, the light is transmitted through each slice of tissue and detected on the other side. So the image has to first be sliced and then imaged. Because of that, there are the typical nonlinear distortions that we also see in histological methods. So it's hard to follow a single axon from slice to slice. Another approach that also relies on the birefringence of myelin, but is slightly different than PLI, is called polarization sensitive optical coherence tomography, or PSOCT. In this case, the tissue does not have to be sliced before it's imaged. So the light is backscattered from the superficial layer of the tissue. And so we image the superficial layer of the tissue, and then we cut it, and then we image the next layer, and so on and so forth. So because the imaging happens before we slice, there is no distortion across slices. And it's not feasible for as large fields of view as PLI. So it would take forever to do a whole human brain with this approach. So it's more appropriate for small samples, but it gives us undistorted data across slices. So this is a method that my collaborator Hui Wang at the Optics core at the Martino Center has been really at the forefront of developing. And we have done some studies that I'm going to show where we compare this to diffusion orientations. So because, as I said, there is no method that can give us the whole ground truth for the entire brain, it's important to use converging evidence from multiple validation approaches. And by converging evidence, in our case, we care about, which method is more accurate than which. How should I acquire my data? Should I acquire, a lot of directions or high B values or higher spatial resolution, etc. So we have, in our lab, we have been following two different approaches. One is using anatomic tracing in collaboration with Suzanne Haber, who's an expert in tracer injection studies. And we are collecting data where we have ex vivo diffusion MRI done on the same non-human primate brains as she has done the anatomic tracer injections. And this allows us to validate diffusion MRI tractography by comparing it to anatomic tracing in the same brain. These data, we've done our own studies, but also we've shared it with the community as part of the Iron Track Challenge, and I'm going to show some results of that. So prior studies, there have been a few that used anatomic tracing and compared it to diffusion MRI, and I'm showing them here in terms of the B value and the spatial resolution of the diffusion data that was used. Most of these compared only the terminal, so only the connectivity matrix is A connected to B, and not the full trajectory of the axons. Are the axons getting there? Is the tractography getting from A to B in the right, along the right trajectory? And that's because most of these studies did not have the tracer injections and the diffusion data in the same brain. So they used existing database like the COCOMAC database that has information from prior tracer studies on is A connected to B. So that's why they could only compare the terminals. Most of them also compared anatomic tracing and diffusion MRI from different brains. So this adds an extra layer of potential variability. And of the ones that had compared the two modalities in the same brain, they were all done in the motor cortex, which is a pretty well characterized set of fibers. The data that I'm going to talk about that we used also in the Iron Track Challenge, we have anatomic tracing and diffusion MRI in the same brains. We have injections in different areas in the frontal cortex that follow these very complex different routes from the frontal cortex to other areas of cortex as well as the subcortex. And we have very high resolution, high angular resolution data, 500 directions, a Bmax of 40,000 and 0.7 millimeter isotropic resolution. I should point out that ex vivo in fixed tissue, the B value has to be about 4 times what it would have been in vivo, because the diffusivity of the tissue is lower. And so we have to increase the B value to get the same contrast as we would in vivo. So when you see 40,000 ex vivo, that's similar to about 10,000 in vivo. So some results from the Iron Track Challenge. It was organized in 2 rounds. In the first round, the teams were free to choose any methods they wanted for pre-processing, tractography, and post-processing. And in round 2, I will explain why we harmonize the pre and post-processing across all methods to focus on differences that are due to the orientation reconstruction method and the tractography method. In both rounds, there were a training phase and a validation phase. In the training phase, the contestants tuned their methods, their tractography pipelines, to achieve optimal accuracy. And that's with respect to area under the ROC curve on one injection site. So this was an injection in the frontal pole. So they were able to upload their tractography results, get their ROC curve and the area under the curve, and then potentially change their methods, re-upload to see if they improved. So that was the training phase. Once they finished that phase and they got the best results they could, they used that optimized pipeline in another data set from a different animal with an injection in a different area of the brain, in the ventrolateral prefrontal cortex. So the goal was to see if you optimize for one seed area, do you also get optimal accuracy for another seed area? Interestingly, we found that for most of the teams, the performance was much worse on the validation than the training case. So optimizing for the seed area in the frontal pole did not mean necessarily that the results were optimal for the ventrolateral PFC. There were only 2 teams that were the exception that had pretty good accuracy for both the training and the validation case. And so then we asked in round 2, we asked the teams to use the same pre and post processing as those 2 teams that achieved good robustness to see if the good results of those 2 teams had to do with the pre and post processing, or if it actually had to do with the tractography method and the orientation reconstruction method. An interesting result was one of the 2 teams had used just a simple Gaussian filter for post-processing the tractogram. And the other of the 2 teams that had good robustness in round 1 had used a priori anatomical ROI. So based on knowledge from the anatomy, from prior tracer studies on where these seed areas project to. And it turns out that when all the teams used these 2 post-processing methods, the post-processing with the simple Gaussian filter that is completely agnostic about the anatomy improved accuracy for most of the teams, and it also improved robustness to seed area. So it decreased the difference in accuracy between the 2 seed regions in the frontal pole and in the VLPFC. And it performed pretty similarly to using the anatomically informed inclusion ROIs. So it's interesting that this very simple post-filtering of the tractogram can actually improve the results quite a bit. It was maybe a surprising result. So which methods perform better? This is both from our own studies that were published in an article in Neuroimage this year, as well as from the Iron Track Challenge, where we opened up to the community using the same data. Overall, we find that all else being equal, probabilistic tractography has better accuracy than deterministic in terms of the true positive rate at the same false positive rate. So the ROC curves that you see here on the left, these shaded areas, the green one and the red one, are the areas that include ROC curves that were obtained with many different Q-space sampling schemes like single shell, two shell, DSI, reconstruction methods, different types of methods for getting the ODF or the crossing fibers, etc. So overall of these different orientation reconstruction methods and Q-space sampling schemes, all else being equal, probabilistic does better than deterministic. In the Iron Track Challenge, we saw a similar effect, particularly for the validation case, where the teams had not optimized their tractography pipelines for that seed area. Overall, the area under the curve was higher for the probabilistic methods than the deterministic methods. And there was also quite a bit of variability for different orientation reconstruction methods. And then the other interesting question is which areas of the brain and what type of fiber configurations are challenging for all methods. And what we found, again, both in our own studies as well as in the results of the Iron Track Challenge, is that these areas where errors occur consistently across different tractography methods tend to be areas that cannot be modeled well by processing. So areas where you have turning fibers, branching fibers, fanning fibers, etc. And that is to be expected because the ODF-based methods are essentially trying to solve the crossing fiber problem. And we have gotten very good at solving that problem, but not so good at solving everything else that can exist in the brain. So that was the one approach that we have followed with anatomic tracing in non-human primates. And the other approach is in human tissue using polarization sensitive OCT in small human samples. And here we are validating not tractography because this is done in small samples, but the diffusion orientations. We compare them to direct measurements of fiber orientations from the optical imaging. This was a study that was published by Robert Jones et al. In Neuroimage last year, where he compared a set of different Q-space sampling schemes like single shell, multi-shell, as well as DSI, at different levels of spatial resolution, going all the way from the 0.25 millimeter, that was the native resolution of our ex vivo diffusion data, all the way up to 2 millimeters. That's more typical of in vivo. And trying to figure out how does the B value, the number of directions, and the spatial resolution compare to the accuracy of diffusion orientations when compared to the ground truth orientations from the optical imaging. So what we do is we first do a whole brain or whole hemi scan in a human scanner at low resolution. And this allows us to identify the tricky areas where there are a lot of complicated fiber configurations. And then we physically section those areas out of the hemisphere. We perform a high resolution scan at 250 micron resolution in a small bore scanner, a 9.4 Tesla scanner. And then we perform the optical imaging in these smaller samples. And you'll see here, you can appreciate how, because we don't have the distortion in polarization sensitive OCT, we don't see distortions between slices because we first image each slice and then we cut. So this would be as opposed to PLI or histological methods. So some of the results from Robert's studies and analysis of variance showed that the biggest effect was the one of spatial resolution, followed by the orientation reconstruction method, and then by the Q-space sampling scheme. Specifically for the spatial resolution, the accuracy deteriorates between 1 millimeter and 2 millimeter voxel size. And then it stays relatively stable. So this is good because it tells us that if we can get down to 1 millimeter with newer acquisition methods, then we can get as good as we can get with these methods in terms of the spatial resolution. The number of directions has shown here on the right has less of an impact in the accuracy. And interestingly, very high B values make little contribution to orientation accuracy. So very high B values would be similar to the 10,000 B values in vivo that we get from the connectome scanner. Again, these were ex vivo data, so we went up to 40,000, which is roughly equivalent to 10,000 in vivo. So great importance of spatial resolution, suggesting that if you have some time to spare to collect your data, it's better to make your voxel smaller than to collect a ton of directions. In terms of the most challenging areas across different orientation reconstruction methods, we found that again, branching is very challenging, again, because these methods are targeted at modeling crossing fibers. And also interdigitated crossings are harder to resolve than areas where the fiber bundles that are crossing are separable rather than, interdigitating. And so we are continuing these studies. There was another paper by Robert that came out in your image this year, where he showed that in terms of the Q-space sampling scheme, a compressed sensing DSI scheme can be used both to reconstruct the full DSI data and to resample on Q shells. So with an accelerated 171 direction scheme, we can get the benefits of both having multi-shell data and having DSI data, which does seem to make a bit of a difference in terms of the accuracy. And I will end here and take any questions and thank the people who are doing the hard work.
Thank you so much, Dr. Yendiki. This is fascinating. It's almost like a different world to me, coming from like T1 and fMRI,
Yeah.
It is so much harder than I realized, actually,
Sorry, go ahead.
So it is so much harder than I actually imagined, so it's amazing how much work is going into improving the accuracy of the results. It's just fascinating to me personally. So
it's good to know that things we're getting right. So it's not all garbage. But now it's get the finer so where are we trying to get the finer details from? We can get the big details correctly, but it's the smaller side roads that are trickier.
Right. So do the audience have any questions? Maybe otherwise I'll start with a tough question. So I think you would know who this question was asked in another meeting we were both in. So I'll not name them, but I would say, does this matter?
This being what?
All this QC and validation, in the final analysis of the results, for example, in biomarker applications or other popular applications of the DTI-derived measures,
Well, for the QC, I showed you an example where it does matter, right? Where the motion can introduce false findings. You might find, if you don't take it into account, you'll find a difference between groups that is not really there. It just has to do with emotion. So it matters to be able to quantify the quality well and to include it in the analyses.
Yeah, no, I believe it matters. I'm just trying to see where you get that.
I think you show some specific examples, and I only mentioned like our study and another one that was doing the connectivity matrix, the graph theory stuff, but I'm sure there must be others that have shown that you get different results if you account for motion and if you don't.
Yeah, not at the individual levels. I think there's still a lot of work to be done in specific applications such as biomarkers. How bad of a data can we use to still make the correct diagnosis?
Right, yeah.
There may be good differences, but can we still use that at the individual level to diagnose them right?
Yeah, so
clinically,
I think where there may be like a gap in the literature is to do this type of, like the group study that we did a few years ago, to do sort of an individual prediction analysis and see whether the motion affects the results.
Yeah, exactly. So yeah, I think some things we can work around, some loss of quality, or some we can, but we don't know what they are because they haven't been systematically studied.
Right. Yeah. I mean, ultimately, the best way to convince someone that something does or doesn't matter is to show like hard, plots, results.
Yeah.
So in principle, yeah, I mean, it should matter, but then somebody might say, well, if it's if you have like 5,000 subjects, maybe on average it doesn't matter. But
yeah,
I think that, yeah, for the individual, definitely that's a whole different story.
Yeah. Jeff and Jenna, do you guys want to ask the questions, or should I read it out?
So this was after the tractography. So the tractography was run, and then it was converted to a visitation map, like a volume, and then the Gaussian filtering was done there.
Right. Jenna was saying she also thinks that things such as DMRI being used in surgery prep leave very little room for error. Yeah, see. Yeah, there, I guess, nobody would dispute the need for that.
Yeah, especially if you're trying to, target a very specific, if you have a very specific target. I mean, I think maybe for bigger things, like don't cut the corticospinal tract, maybe I think that I think that can be done with the data that we have and with the methods that we have. But then if you're trying to do more accurate targeting, yeah, it's important to have high quality individual data. I absolutely agree.
Any other questions from the audience? Don't hesitate. We're all a friendly group. Nothing is off the table.
And don't forget the brain hack. Yes. Hope to see you there.
Anastasia, I had one question. Can you speak a little bit more fully on the trade-offs that you were speaking about at the end related to the spatial resolution of the acquisition versus the higher B values versus the angular resolution? And it seems that there's some kind of sweet spot that you were trying to allude to, but I didn't get a clear idea of where you thought that sweet spot actually lived and where what that domain looks like.
Yeah, so it seems like the in terms of the spatial resolution, there was a sweet spot of around 1 millimeter, which is higher than most studies are able to collect right now. But then the number of directions, like going from 64 to 128, something like that, it didn't make a ton of difference for most of the orientation reconstruction methods. Again, this differed a little bit between methods. But for most of them, it didn't make as much of a difference as going from 2 millimeter voxels to 1 millimeter voxel. And then in terms of the B values, I would say that the very high B values, like up to 10,000 or whatever, they don't seem to contribute to the accuracy of the ODFs. They're potentially interesting for microstructural measures, microstructural modeling, but in terms of the accuracy of ODFs, they don't seem to have a big impact. Now, this doesn't mean that there isn't any information potentially in those higher B values about the fiber configurations. It's possible that because we reduce the data down to an ODF, this crossing fiber model, maybe we discard the information that's hiding in those higher B values. And so maybe there is something useful there. It's just that with the methods that we have right now that are focusing on the, resolving the crossing, those higher B values are not that important.
Thank you. So when you were talking about combining it with DSI and so on, how does that play into the resolution of whether the ODF is accurate or not? Because you seem to be combining two different methods to try and attack the problem.
So there it had to do more with how the data was collected. So with DSI, you're collecting the data on a grid in Q space, and with Q shells, you're collecting them on a shell or two shells. So with compressed sensing DSI, which is an accelerated version of the full DSI, you're basically randomly picking which locations on this grid you're going to collect, which of all the 500 directions you can collect. So you can actually undersample quite a bit. So just 1/3 of the full 500 directions that you need for DSI, and get both accurate DSI reconstruction and also be able to resample the data from this random sampling onto shells if you want to use methods that rely on having data on shells. I don't know if that makes sense.
Actually, that does. Thank you very much. That clarifies it immensely. Thank you.
Thanks for the great questions.
Any other questions? So one of the things I want to do maybe in the next brain hack or later is to help with individual QC in a more visual fashion. Just so after they acquire the data, they can open the data and look at it. And I know that there has to be some amount of pre-processing before you can actually identify the issues with the diffusion data, but are there any simple things with some reasonable amount of processing that we can implement to make it easy for people to detect issues with their data?
Yeah, so because with diffusion data, you have tons of volumes, it's slower than with T1s, right? Because with a T1, you're scrolling through one volume.
Yeah.
There you have multiple ones. So if there's a way to identify, the ones that might have bad slices, and then take you to those volumes, that can shorten the whole process.
Right. Yeah, I did implement something that animates through all the B values. That way you can easily check whether they are misaligned. That's one of the ways to do that. Okay, cool.
Yeah. The question is if it's just flashing through, how would you point to the ones that are bad?
Yeah, there is ways to implement to paths and whatnot, but at least I think people don't look at their data as much as they should.
Yeah, I agree that.
So I'm just trying to find ways to build assistive tools to make that as easy as possible, right? Especially with these big data sets, the likelihood that they go through all that thousands of subjects is like very low. They need tools, they need simple metrics.
Yeah, you need a way to find some candidates, like candidate
Yeah.
direction, candidate subjects.
Right. Yeah, like your TMI index would probably help in that sense too, right? So
To find this, yeah.
Yeah, and another question I had is there a tool independent quality checking metric slash criteria? You know, like this, we talked about Dracula, Eddy, Dropout, and a few other things, right? So I would ideally, it's my personal opinion to have diagnostic slash QC be separate from the processing tools themselves, right? In order to just think about the issue itself rather than what produced it, right? So any comments on such tool agnostic checks?
Yeah, I mean, it's even our quality measures are estimates, right? Based on some noisy data. So I don't know what would be a way to not having, like, the way you extract your measure will always matter, right? So I guess I'm not sure how to answer that.
Yeah, something to think about, I guess.
It's one thing I haven't looked at so much is, now with these HCP and ABCD style data that have these higher B values, how good are these measures that I had looked at, a few years ago on much lower B value data? How good are they at identifying those outliers? Eddy also has a way of identifying outlier slices, and you can tell it to fix them or not. So that's another more recent development. Yeah, so I think that it also probably outputs some additional measures of outliers and stuff like that would be worth looking at.
Yeah, I guess that sounds to me like there needs to be a lot more discussion on this topic in terms of, some giving guidance, like really practical step-by-step guidance to users.
Yeah.
You have your diffusion data, how would you go about making sure it's all good for analyses and publications and whatnot? So yeah, we'll get more speakers and see if they can provide some guidance. Yeah. Thank you so much. If there are no further questions, thank you for doing it the day after you got your booster shot.
Still not fully recovered.
Yeah. Yes. Yeah. Yes. This was fantastic talk. I'll share the video and send you the link. Yeah.
See you at the brain hack. Bye.
Bye. Thank you.